analog circuit in action. Here we have one multiplier, another multiplier, and the capacitors are 33 nanofarads. We also need plus and minus 15 volts power supply. It was an effort to solder analog multipliers to deep sockets. Actually, analog multipliers in deep cases were fake and were overheating and did not work. This is famous circuit by Horowitz and Hill, and I was quite confused how resistors are calculated. For example, here is 100 kilo ohm, 100 kilo ohm, and feedback is 1, and it is not 10 times. Glenn's staff helped understand things better. Simulation shows that it's actually the same resistor values as in Horowitz and Hill, except resistors here 20 kilo ohm and 20 kilo ohm. It appears that in MATLAB one can simulate with just the 3 lines of code. Here the function is defined, here is coordinate x, y and z. And we solve using Runge-Kotta solver and plot. I use free alternative of MATLAB called Octave, and we can rotate the figure, and then we see that scaling is 40 and 20. This is more than operational amplifiers can give out. In OPamp circuits, first law is that both inputs are at the same voltage. Here it is 0 volts, and that currents at this node should sum and equal to 0. And using Ohm's law, we can say that current is voltage divided by resistor. And finally, could simulate the result by Horowitz and Hill analog op-amps. And here we get voltage 5 volts and 2 volts, which is in range of operational amplifiers. And in the function, we divide voltage by 100 kilo ohms and another voltage by 100 kilo ohms. Here we divide voltage by 35 kilo ohms. Here we divide by 1000 kilo ohms. And analog multipliers, they divide voltage by 10, and then we divide by 10 kilo ohms, so this gives factor of 100. And for Z, we divide analog output by 374 kilo ohms, plus multiplication divided by 10 and divided by 10. So now analog signals match calculation with MATLAB.